All right, so we're going to deal with rational functions tonight, which is fractions, basically. Everybody's favorite thing. Fractions. So rational functions, there's quite a few things that we're going to be finding. So you're going to be kind of thinking, gosh, he's throwing a lot at us here. And I am, but it's all things that you can find if you'll just follow some simple rules and a process of how to work through a rational function. Okay, so when you're dealing with a rational function, we're talking about some polynomial on top of another polynomial. That's all it really is. And with that, you got some basic things we've already done. Domain. Get that by set the denominator equal to 0. That's what we need to do, okay, to find the domain. The next thing we want to do is simplify. And that involves factoring. Factor top and bottom, and then cancel what'll cancel. Okay. Not always going to simplify, but sometimes a factor will cancel out, and we can, we see what happens there. From that simplifying, that's when we get wholes, and then with that gets us into asymptotes. And asymptotes are these imaginary lines that kind of guide the problem, the graph in what's going on. And there's 3 different kinds of asymptotes that we'll be finding. One of those is the vertical. Denominator equal to 0. Now, this is the denominator of the simplified form. Okay. It should match at least some of the domain. It won't always match the entire domain, but it should match very closely to our domain out of that. And then, so that's what you're going to do to find the vertical. The horizontal has some rules. So horizontal asymptotes only occur if the degree of the numerator is less than the degree of the denominator. If that's what's happening, the top part has a smaller degree than the bottom part, then the horizontal asymptote is y equals 0. Okay. Example of that would be a function. Maybe you got x squared plus 9x minus 3 over x cubed plus 1. Numerator has a smaller degree than the denominator. That would give us a horizontal asymptote of y equals 0. I picked that one because it doesn't simplify any. If we had some simplifying that would happen, we'd need to do that first. That one doesn't simplify. So horizontal asymptote on that one because is y equals 0 because the degree of the top is 2, the bottom is 3. As long as the top is smaller than the bottom, it's y equals 0 for a horizontal asymptote. Next occurrence of a horizontal asymptote is if the degree of the numerator is equal to the degree of the denominator. then the horizontal asymptote is at y equals a over b. That's the ratio of the leading coefficients. I'll show you an example of that real quick. So f of x, 3x squared plus 5x minus 7 over 4x squared minus 2x plus 13. Pick those two because they don't simplify, they don't factor at all. It's not going to simplify. The horizontal asymptote would be at the ratio of the leading coefficients, y equals 3 over 4. That's our horizontal asymptote. And I abbreviate that HA. Aha. 3/4. Okay. If the degrees are the same. Those are the only times horizontal asymptotes occur, is when the degrees do that. Okay. The third type of asymptote that we would have is what's called an oblique asymptote. But you may hear me slip up and call this a slant asymptote. That's what they were. That's what I grew up calling them. Oblique or slant asymptote. You may see them if you Google oblique asymptote. You may find websites that call them slant asymptotes. It's the same thing. That only happens if the degree of the numerator is one more than the degree of the denominator. Then use long division to get a little extra space here. One more line. Find y equals mx plus b. So an oblique could happen if you had f of x is equal to maybe something like x cubed plus 27 over x squared plus 9. An oblique would occur for this one because the degree of the top is 3, the bottom is 2. Obliques and horizontals never occur together. It's important to know that if you have a horizontal asymptote, you will not have an oblique asymptote. Star oblique and horizontal do not occur together. Important to know there. Okay. All right. Now, inside of this, we're also going to find intercepts. So a lot of the same things we found for every type of function we've dealt with the entire course. X-intercepts. That function equal to 0. Y-intercepts, or Y-intercept for each one, be plug in 0 for X. So Y-intercepts plugging into 0 for X into the original function. X-intercepts are setting the thing equal, or not necessarily the original, the simplified version works fine. To find the x-intercepts, are setting the simplified version equal to 0. You use the simplified version just because it's smaller, it's easier to use. And then One last thing that we need to check on is decide if the graph crosses the asymptote. And that's only for horizontal or oblique. HA for horizontal asymptote, OA for oblique asymptote. We're going to decide that for each of these problems. So a lot of things we're going to find for each problem, but shouldn't be too daunting of a task. We know how to do all of these things. We just got to figure out how to get it from one place to another. So if you came in late, you're going to see everything that we talked about as we go along here. Okay, so let's look at some examples and do all these things for them. So example A, here's our function f of x is equal to x squared plus 7x plus 12 over 4x squared minus 1. So the things we're going to find, domain is the first thing we're going to find. We find the domain first because we want to get that from the unsimplified version. Okay, domain always happens first from the unsimplified version. So how do we find domain? Set the denominator equal to 0. That's that red flag that we talked about back in chapter 3, the x in the denominator. So we're setting that denominator equal to 0 and solving it. We happen to know that 4x squared minus 1 factors as 2x plus 1 and 2x minus 1. It's a quadratic, so the methods for factoring a quadratic are what we're using there. And then I could set each of those equal to 0. So x does not equal negative 1/2. X does not equal positive 1/2. And I'm fine with you writing it in this form. The set notation instead of interval notation there is fine. You're just fine for that. All right. So there's our domain. So what we're going to be looking at here is the factored form. So I've already factored the denominator, 2x plus 1, 2x minus 1. The numerator, does it factor? Yeah, it does. It's x plus 3, x plus 4. I want to look at that factored form because right after I find the domain, I want to try to simplify that fraction if at all possible. Do any of these factors cancel? None of them match, so they don't cancel. So there's nothing that simplifies on this one. Sometimes there will be, sometimes there won't be. There's just not on this one. So from there, the next thing on our list was the wholes. There are none. If there's a factor that cancels, that's when a whole happens. We'll see that in the next couple of examples. We'll see what happens there. So there are no wholes, but then we start looking at our vertical asymptotes. Vertical asymptotes come from the denominator of the simplified fraction. Well, we didn't have anything simplify on our fraction, so the vertical asymptotes are going to match the same thing as our domain, but they're equations of lines. So it's x equals positive 1/2 and x equals negative 1/2. We'll look at this on a graph in just a little bit once we get all these pieces built. So vertical asymptotes, since nothing canceled out, they match the same thing as our domain did. If something cancels out, you may lose part of that, things from the domain may not show up as vertical asymptotes. Okay. Next thing would be horizontal asymptotes and oblique asymptotes. So what's the degree of the top? Degree of the numerator. 2. It's the degree of the denominator. 2. So they're the same. That means what about horizontal asymptote? Look back at our rules here for horizontal asymptotes. if the degree of the numerator is equal to the degree of the denominator, it's the ratio of the leading coefficients. So here's an example of that. Let's look at our problem. Our problem had leading coefficients of 1 and 4. It'd be y equals 1 over 4. It's coming from that, right? That's where that's coming from. Okay. The 1 from the numerator, the 4 from the denominator. Okay. If we have a horizontal asymptote, what's that mean about obliques? There's not one. Never will be one. Oblique asymptotes, none. Okay. Next thing we want to do is finish off the things with the asymptotes. So we want to decide, does the graph cross y equals 1/4? Okay, crossing that horizontal. So does f of x cross y equals 1/4? So the way to find that is set the problem equal to that. So since nothing's simplified, I'm gonna go back to the original y or x squared plus 7x plus 12 over 4x squared minus 1 is equal to 1/4. I'm just going back to that unfactored form since nothing's simplified because I'm going to have to cross multiply to solve this. So when I cross multiply, bottom times top, I get 4x squared plus 28x plus 48 equals 4x squared minus 1. And then I need to try to get like terms together here. Subtract 4x squared. The x squareds are canceling out. So that means I can take 28x plus 48 equal to negative 1. Subtract 48. 28x was negative 49. And divide those. And I get an answer. Negative 49 over 28. If I get an answer that has x equals a number, then the answer to that question is yes. Okay? So I'm asking, does it cross it? Yes. Where it crosses it is where this x is. This is x equals. Okay? We'll see some in the future here as we're going along that they don't cross. And that's okay. We're just trying to answer that question. So you set the original problem equal to your horizontal asymptote or your oblique asymptote, whichever one you have, and try to solve it. It's cross multiplying is how you're going to do it each time. All right? So that took care of everything with our asymptotes. The last thing on the list is intercepts. So let's get the intercepts. Intercepts. I'm going to do x and y's. So to get the x-intercepts, we're going to set the entire problem equal to 0. And I'm going to go ahead, I've got x squared plus 7x plus 12 over 4x squared minus 1 equals 0. What happens with that in the denominator when I cross multiply or multiply by the denominator? What's 0 times 4x squared minus 1? 0. So the shortcut that I'm trying to get you to see here is that it's really just the numerator that you set equal to 0 to get the x-intercepts. The denominator really doesn't have anything to do with the x-intercepts. Okay. So to get the x-intercepts, set the numerator equal to 0 and solve that. So we've already factored that once. X plus 3, x plus 4. So we have x-intercepts at x equals negative 3 and x equals negative 4. So those ordered pairs would be negative 3, 0 and negative 4, 0. And then to find a y-intercept, plug a 0 in for x. Ends up being 12 over negative 1, which is negative 12.
So the other intercept at 0, -12. So there are 3 intercepts that we happen to have for this particular problem. Won't always have that many intercepts. Won't always have any x-intercepts. And might not have any x-intercepts. Okay. Now let's look at this on a graph to relate all of this stuff back to something that makes sense. So if I graph, reopen now, that original problem, and I'm going back to the original when I go to look at the graph. So I've got parentheses x squared plus 7x plus 12. Close the parentheses, divided by, and then another set of parentheses, 4x squared minus 1. Hit graph. All right, so this is what I want to show you. We've got vertical asymptote at -1/2 and +1/2. There's the -1/2 right here. The +1/2 right there. We can see that guides that graph into becoming pretty vertical in those spots. We have a horizontal asymptote at y equals, what's it, 1/4? Is that right? And that's real close to the y-axis, or in the x-axis there. And then, so we can see how that's guiding that to be pretty flat on the bottom. All right? So that's what those asymptotes do. Intercepts, we got x-intercepts. We can see where it's hitting the x-axis. We can see where it's eventually, there's a piece of the graph we don't see here in the bottom. You zoom out. Because remember, we got a y-intercept at -12, so I'm going to have to zoom out a little bit so you can see that bottom piece. There's this bottom piece here. It's a real skinny parabola-looking shape in here. And there's some stuff going on. That's where that y-intercept's going to happen at. So we can see those things happening. All right. So that's what we're doing for these 2 sections. Let's look at another problem and see if we can pull something off with it. For the intercepts. All right, there you go, right there. -3, -4, and then 0, -12 for the y-intercept. All right, good. All right, so let's look at this one. Example B. Let's call it g of x is equal to x squared plus 7x plus 10 over x cubed minus 25x. So again, before we do anything, we're going to find the domain of this problem. So how do we find the domain again? Right. So x cubed minus 25x equals 0. And there's other ways to solve this cubic. Factoring is the method you want to go toward because you want to factor it anyway to simplify your fraction. So that's why you want to try to factor here if you can. GCF of that would be x. Lose the x squared minus 25. But x squared minus 25 will factor again because it's a quadratic that goes x plus 5, x minus 5. So our domain, our x, can't be 0. X can't be plus or minus 5. So we get x such that x does not equal 0 and plus or minus 5. That's a fine way to write that. We could do integral notation for that. It's kind of lengthy and that doesn't really help us much on this particular type. And I'm fine with set notation on this stuff. There's enough work to do that we can just leave that there. All right. So that's going to help us in simplifying here. So we need to factor the numerator so we can simplify. So we need something that multiplies to be 10 and adds to be 7. Yeah, x plus 5, x plus 2, And then what cancels out? Those x plus 5s cancel each other out. That's where the holes occur. When you have a factor that cancels, that's what creates a hole. So we have a hole at x equals -5 because it was x plus 5. So we need to find that particular function value, and we're going to the simplified version. Simplified version is x plus 2 so it'd be -5 plus 2 over -5 times -5 minus 5. Yeah, minus 5. That's going to get us an ordered pair where this empty spot occurs. So we're finding the y value that goes with that x value that has a hole at it. So it'd be -3 over +50. Is that right? Yeah. -5, -3 over 50. That's important to know. One of the key things that we want to find out here. There's a hole at that. What that means is, like, remember we did piecewise defined functions and there was these empty circles at spots? That's an empty circle when we graph this problem. There's an empty circle there at that point. That's what that means. The hole. Now, related to that are the vertical asymptotes. So that comes from the denominator of the simplified fraction. So the simplified fraction has two pieces left in the denominator. It's got the x and the x plus 5, or x minus 5. The x plus 5 is gone. So the vertical asymptotes are at x equals 0 and x equals +5. Only two of them, even though the domain had three pieces. Because we had a simplifying part of the fraction, we lose some of that when we go to do the vertical asymptotes. Okay. The next thing to do is look at horizontal and obliques. What's the degree of the top now on the simplified fraction? What's the degree left up there? 1. We canceled out one of the x's. What's the degree left on the bottom? 2, because you got x times x minus 5, so that would be x squared. So the top is smaller than the bottom. So y equals 0 is a horizontal asymptote. What's that mean about oblique asymptotes? There are none. Those never occur together. Because the degree, the way the degree works, the degree has to be one more on the top than it is on the bottom for an oblique to even occur. In this case, the degree was smaller on top than the bottom, so obliques can occur when that's happening. The degree at the top has to be one more than the bottom for an oblique to even show up. All right. Next thing we want to decide is, does it cross y equals 0? So take the simplified version if you want to. X plus 2 over x times x minus 5. Set it equal to 0. Does g of x cross y equals 0? We're going to get two birds with one stone when we do this, because we get x equals -2, so that's a yes. And when we set the whole problem equal to 0, what else are we finding? X-intercepts. We get two birds with one stone. We get an x-intercept at -2, 0, and we know it crosses the horizontal asymptote of y equals 0 because we got an x equals right there. So this is normally what we would do to find the x-intercept, set the whole thing equal to 0. Just so happens that because the asymptote was there, we got that for free. Always love when that happens. Okay. The other intercept to find would be the y-intercept. So this is g of 0. So 0 plus 2 over 0 times 0 plus 5. But that ends up with division by 0. Is there any way that can happen? Can we divide by 0? No. So there's no y-intercept. That's what that means. No y-intercept because we got division by 0. Okay. So the only intercept we have is at negative 2, 0. Okay. We could look at the graph. And I'm going to go to the graph of the original problem just so we can see the hole and all that stuff that occurs. So when you check your graph, you want to check it with the original problem. X raised to the third minus 25x. Hit zoom 6. This one doesn't, it all occurs real close to the. We got 3 pieces here. We got the x equals 0 asymptote. We got the x equals positive 5 vertical asymptote. There's our y equals 0 horizontal asymptote. And if we checked that x value for that hole that occurred, remember that hole was at negative 5. If I type that in, if I hit trace and then do negative 5, not positive 5, but negative 5, notice it doesn't give me a y value because that's a hole in the graph. It doesn't exist. We know where that hole occurs. We know the y value that should be there because we worked it out. But it doesn't give me one there because that is a hole in the graph. It's an empty circle there. So it doesn't give me an ordered pair for that. So that's how you can check to make sure you got the correct x value for the hole in the graph. Yeah. So not too complicated here. Just maybe lengthy would be the best way to describe it. Let's look at this one. Let's see. F of x is equal to 6x squared plus 9x over 3x minus 2. Seems simpler, just a little smaller problem, but still some interesting things happening with this one. Okay, so the first thing we want to do is domain. Not quite as much work to find domain on this one. We're setting the denominator equal to 0. X can't be 2/3. That's pretty easy. Domain. The next thing I want to look at is the factored form of numerator and denominator. Numerator will factor with the 3x as the GCF, and that would leave 2x plus 3. And then the bottom part has 3x minus 2. Can I cancel this 3x and this 3x? Why not?
Because that 3x is essential for the it keeps the numerator.
Well, not necessarily about it keeping the degree, but does the factor match perfectly? What's the factor at the top? It's 3x. The factor at the bottom is 3x minus 2. They don't match perfectly. So it's even simpler than what you guys are talking about with the degree. They don't match perfectly, so they can't cancel each other out. Okay, so that 3x up top doesn't have a minus 2. The 3x on the bottom does have a minus 2. They're not the same, so they can't cancel each other out. If that at the top part is what you're saying with if there would have been a minus 2 with that 3x in parentheses, yes, you would have canceled them. But since there wasn't, you can't cancel anything. So no cancellation. So what's that mean about the holes in the graph? None. That sure makes things easier. Vertical asymptotes. Nothing canceled out, so what are they going to match? They'll match your domain, right? Vertical asymptote at x equals 2/3. Horizontal asymptote. This is or oblique. This is where we have to decide which one we have, or if we have either of them. What's the degree of the top? What's the degree of the bottom? What's that mean? Oblique. 2 is one more than 1, right? So that's an oblique asymptote. To find the oblique, you're going to do long division. So we're going to divide 3x minus 2 into, I'm going to go back to the original 6x squared plus 9x, and I'll put a plus 0 there. So we're doing long division, bottom part into the top part. What times 3x will get me 6x squared? 2x. So it'd be 6x squared minus 4x and subtract 2x, or the x squareds go away, and 9x minus negative, so it'll be 13 positive. A little bit more difficult here. 9 minus a negative, double negative makes a plus. That's where I'm getting that. Then that sign change would kind of catch a few of us. Now, kind of tough here. What times 3 is going to give me 13? Here's how you can do that. 3 times what is equal to 13? Can we solve that equation? Divide by 3. So this is plus 13 over 3. That's how you can do that. You can get that number that you can get there. So it happens to be a fraction. That's okay. It's a fraction as a y-intercept. That shouldn't be too big of a stretch for us as far as plotting that. We know that that's 4 1/3 is where that's happening at. So there's our 13x, and then minus 26 over 3. Subtract. Those go away. And we get positive 26 over 3. That part doesn't matter. The only part that matters is this slope-intercept form that's up here. mx plus b. mx plus b. Right there. It's the only part that matters. That technically is our remainder, but it doesn't matter. It doesn't matter what the remainder is. When you're finding an oblique asymptote, you just forget everything else. The slope-intercept part, y equals 2x plus 13 over 3 is our oblique asymptote. And because we have an oblique, that means we have no horizontal asymptote. Long division. I told you guys we're going to have to use it at some point back earlier in we're doing polynomials, and we did long division the first night with that. This is where you need it again to find that oblique asymptote. All right. Next thing is, does it cross? So does f of x cross y equals 2x plus 13 over 3? Well, the only way to decide that is to set it equal to it. So 6x squared plus 9x over 3x minus 2 equals 2x plus 13 over 3. And you're going to need to multiply both sides by 3x minus 2. This side, it cancels out. So that leaves us 6x squared plus 9x on that side. On this other side, we get 3x times 2x, 6x squared. 3x times 13 over 3 would be 13x. Negative 2 times 2x is negative 4x. And then negative 26 over 3. Look what happens. 6x squared plus 9x shows up on both sides. So if you subtract 6x squared and then you subtract 9x, what happens? They both go away. Does 0 equal negative 26 over 3? It does? You owe me 26 over $3. And can I say you owe me no dollars? I could, but it wouldn't be right, right? 0 doesn't equal that. So that means there's no solution to that equation. If there's no solution, that means that it does not cross. So the answer to that is no. A little tougher algebra to do on the obliques than there is with the horizontals, but still doable with that. And a little tougher algebra, but last thing to do with these, this problem would be intercepts. So let's do some intercepts for this. So we got f of x. Let's see, was 6x squared plus 9x over 3x minus 2. Set that equal to 0. That's going to find us which intercepts. The x-intercepts. Good. Ends up being just the numerator that you need. So factor out. We've already factored that once. So 2x plus 3. So we get x-intercepts at 0, 0. So it's 3x equals 0. And then, so that's x equals 0. And then we set 2x plus 3 equal to 0. That'd be x equals negative 3 over 2. And then if we find the y-intercept, let's plug a 0 in for x. End up with a 0 divided by negative 2, which is 0. So that's that one we've already listed, the 0, 0. So those are our intercepts for this graph. 0, 0, and negative 3 over 2, 0. The y-intercept and that other x-intercept, they're the same. So that's at the origin. Okay. Let's do one more. Three x squared minus 9x over x squared plus x minus 12. First things first, you tell me what to do. Domain. How do we find the domain? So x squared plus x minus 12 equals 0. How do we want to try to solve that? Factor it. How does that factor? X plus 4, x minus 3. Good job. So that gets us x plus 4 equals 0, x minus 3 equals 0. So x can't be -4. X can't be 3. There's our domain. What do we do next? Okay, so to simplify, what else do we have to do? All right, so let's factor the numerator. No. We already got the denominator factored. It's x plus 4 and x minus 3. How do I factor the numerator? It's the first thing I should always look for if I'm trying to factor something.
It'd be 3x plus 3. 3 on the outside of the
Mm-hmm.
3x plus 6x minus 3.
Good job. 3x parentheses x minus 3. GCF is 3x. Greatest common factor of 3x squared minus 3x. All right. What happens now?
You get another cancel out x.
Yeah, those x minus 3's cancel each other out. What's that create? Whole at what? X equals 3. We want to find that value. So it'll be 9 over 7. So the ordered pair would be 3, 9 over 7. We're going to find the ordered pair for that whole. You know it exists there at 3. Just plugging it in and working it out. After we found the whole, the next things that we're going to work on together are vertical asymptotes and then horizontal and obliques. So vertical asymptotes. Where is the one or ones? At x equals 4. That's the only thing. Is it positive 4 or negative 4? Negative 4. The only thing left in the denominator was x plus 4. When you said x plus 4 equal to 0, that's what you're going to get. X equals -4. Remember, it matches the part of the domain that you found. Okay? Vertical asymptotes should be found somewhere inside of your domain. It won't exactly match your domain every time, but they should be in there somewhere. Okay, so then the next thing is horizontal and oblique. Horizontal asymptotes. Is there one? Where at? Y equals 3. The degree of the top. Remember, this part's gone. So we have 1 and 1. So the degree is the same. 3 over 1. So that's y equals 3. Horizontal is always y equals. Vertical is always x equals. What's that mean about obliques? None. That's easy. Does it cross? How do we find that? Yeah, put the problem equal to 3. It's equal to a number here. I'm going to make it a fraction so I can cross multiply. 3x equals 3x plus 12. When I go to solve that, all the x's cancel out and I get 0 equals 12. Does 0 equal 12? No, so it doesn't cross that. Because we don't get an answer that says x equals something. Okay. That's exactly right. That's right. It only crosses if you get x equals some number. That's the only time it'll cross. Okay. Last thing, intercepts. How do we find them? Set what equal to 0? Okay, we could set the original problem. I'm going to set you can go back to the original or you can go to the simplified version. I think the simplified version is going to be easier on this one. Because we don't have to do that factor. Remember that the part is already canceled out. That x minus 4 is already canceled out. So it's not going to affect anything. So 3x equals 0 and x would be equal to 0. So there's an intercept at 0, 0. And to find a y-intercept, technically we should do what? Plug in 0 for x. And we're going to see that that's the same. Or x minus 3 is the part that counts. So there's 0 again. That's the same spot. It's a y-intercept, it's an x-intercept, it's the origin, it's both. And so the only intercept we have is at 0, 0. We can verify this by graphing the original problem on our calculator. We can see all of these things happening. Sure. That the intercept part. All right, so schedule for the next week. Let me stop this real quick. I'll